In chemistry, we often use different equations for different applications. In this supplementary video for electrochemistry, we are going to focus on a balanced reduction oxidation equation, which is often referred to as a redox equation. And today we want to focus on being able to identify the two half reactions in a balanced redox equation, understand how acids and bases affect redox potential in a very qualitative way, and also know how to write and balance electrochemical equations using the half reaction method. This is a fairly extensive memorization technique. I think it's worth your while, especially if you're going to stay in chemistry or be a chemical engineer, to know how to do this technique. But beyond that, if you have a reduction half potential table, you'll still be able to do the techniques that you would gain from knowing this method. That's why this is a supplementary video. So let's get started. The first point that I would make is that really, why do you need a method to figure out how to do a balanced redox equation? And the two applications are either batteries or for working with redox reactions in general. And I just want to point out that they're really similar in the sense that if you take a battery, you're going to have two half cells, and in this case we have zinc being oxidized to zinc 2, and that will create electrons which then flow over to the other side of the battery, where in this case copper cations are being reduced back to copper metal, and that's what provides the free energy to drive this. And you can harvest that free energy in a battery. Here's another reaction, which really is just a simple redox reaction. We don't have it set up in a battery cell, but we've dropped iron metal into HCl and hydrochloric acid, and as you know, then the iron would lose its electrons to the protons in the water, and they would turn into hydrogen gas. So once again, there's an oxidation, there's a reduction. These aren't split into half cells. It's just happened spontaneous, and this would explain how hydrochloric acid is able to decompose metals and turn them into a salt, in this case iron 3 chloride salt, and release hydrogen gas. But just to prove my point, what I'm going to do is I'm going to take these two reactions, change their roles, and show you that, hey, you could also set up a battery using the iron oxidation coupled to the hydrogen reduction. And in fact, that hydrogen reduction, as it's set up here with the inert electrode that drives electrons to it and transfers them to the hydronium ions in solution, that is could be coupled to iron oxidizing and creating electrons. And this particular half cell actually demonstrates the standard electrode, the hydrogen H+ electrode that's used as standard potential, half cell potential of 0. And again, I just put in the kind of flow of electrons here. So on one side you've got your oxidation, on the other side you got your reduction, and this could work just like a battery. And consequently, you could go to the other side and not break into half cells and just, drop zinc bars into a zinc cation and copper cation solution, and you could drop the zinc and copper bars in there, and you could still have the same sort of reactions going on that would cause redox to take place. And this is not then utilized as a battery, but you could still have the same sort of chemistry going on. And my point being here is that in either case, you want to focus on the oxidation component and the reduction component. And so consequently, a balanced redox reaction has components that are often we try to think of them as half reactions. So let's just isolate down on the iron and HCl reaction. If you want to take the half reaction at the reduction, you're basically taking protons, adding a couple electrons, making hydrogen gas. So that is what we call the half reaction. And then on the other side, there's the oxidation taking place, which is iron metal going to iron 3+, which is then water soluble. And that releases 3 electrons. And these also are what we would call the half-cell reactions if we want to put them in a battery sense. But how do we get from these half-cell reactions that you see up here, here's the reduction, here's the oxidation, and get up to this balanced overall equation? What kind of ties those together? Well, one of the things is conservation of mass. Did you maintain atoms? So let's just look at what we have on the overall reaction up top here. And if you look, we do have an imbalance in the chlorine ions, right? So you might have to make some changes in here. And as we've learned in balancing chemical equations, even in General Chemistry 1, you never change the superscripts because that really describes the complex, or in this case, the charge balance. And so, but you put coefficients in front. So we get this all done. Now we have the conservation of mass. It's taken care of. And then the second piece that you want to take care of when you're doing balanced redox equations is, did you conserve electrons? In other words, for every reduction event, there's an oxidation taking place and vice versa. And if you'll look in our half reactions, you'll see that there's a mismatch in the number of electrons. In one case, the reduction is requiring 2 electrons and the oxidation is releasing 3 electrons. So what you need to do is actually balance that out. And it's okay to multiply those up all the way through the equation by a factor. In this case, a factor of 3 on the reduction and a factor of 2 on the oxidation. And then consequently, you would have works. Another comment I would also make is that as we learned back in thermodynamics, usually when you multiply through on an equation as we did here to balance out our half reactions, you usually multiply through the energy by the same amount. But in this case, you don't do that. This is thoroughly explained in my other videos on YouTube that are specifically tied to electrochemistry. But the number of electrons that you have quantified here is actually tied back through the Nernst equation, some other calculations you do earlier, but for right now you don't usually multiply through by the reduction potential. The reduction potential in essence represents the potential energy of getting from one species to the other, regardless of how many equivalents you do there. And then when you talk about the equivalents or the moles of a material that you take through this process, that's calculated, that's brought back in with other equations we use in electrochemistry. So that's just a slight kind of heads up, watch out for that. But the last piece of just equations in general is the charge balance. And in this case, it looks like it is. The cations are paired with anions. It's not really realistic that you have an aqueous charged solution that's positive in nature or negative in nature. And so for this particular equation, if we broke it down and we broke out all the anions and all the cations, okay, this is an overall ionic equation, you would see that all the reactants have a net charge of 0 and all the products have a net charge of 0. And now I'm just pointing this out to kind of tie it back to your General Chemistry 1. But I do want to make the note that this is not always followed with balanced redox equations. In other words, it's not always necessary to do to answer all the questions you may be trying to solve for. But at some point, this is happening in reality. And I'll kind of tie that together on a different equation we do here in a minute. So now let's talk about doing redox in acids and bases, so we understand something. And the take home here is generally, in the qualitative sense, whenever you do redox in an acid or base, it'll change the potential at which this occurs. So here's an example. If I put copper in aqueous HCl, there would actually be no reaction. And so if we look at our half reduction table, we see why that is, because basically what we're wanting to do is take copper and oxidize it to copper 2 plus. But if you'll look, that copper oxidation is above the actual reduction of hydrogen. And as we know, in order for these to be spontaneous, the reduction should be above the oxidation. So here's another reaction. So this is without any kind of acid and base influence. If you were to drop a sodium nitrate solution on top of copper, once again, there would be no reaction. Now, I don't have the half reduction calculations for that, but this is just observation. But if you put copper in the presence of nitrate that's in an acidic environment, then all of a sudden the reaction changes, and there is a reaction where nitrogen monoxide is formed, and copper is oxidized to copper 2 plus in solution. And the reason for that, you can see, is that nitrate in the presence of an acidic environment actually has a fairly decent reducing potential, and that reduction is above the oxidation of copper, so therefore this reaction does occur. So that reduction is above the oxidation of copper, so this reaction does occur spontaneously. I've got a little picture of this. Here's a penny, and the copper is being dropped in concentrated nitric acid, and immediately you can see that there is a nitrogen monoxide. It's a brown poisonous gas. It forms above the surface. The copper is actually decomposing. We can see the evidence of that because copper nitrate in solution is, the copper 2 ion in solution is green, so you can see the solution turning green. And if you let this run, it'll literally decompose the face of the penny, get into the zinc. That reaction obviously will run quickly because the zinc's much more active, and as a result this penny will totally solubilize and turn into its metallic ions. So just once again, the take home here, besides being a cool demonstration, is that presence of an acid or base, the reduction potential of materials changes. So you need to be aware of that. But that does give rise to some complicated half reactions when you're trying to balance a redox reaction. So now I'm going to demonstrate how to get to a balanced redox equation for this reaction using the standard reduction potential table. We're going to start with the half reduction table, and I pulled out the parts that are necessary up here at the top. And if you take the half reactions and you want to look at the reduction, it basically would be the nitrate, which would have a +5 charge on the nitrogen, which changes to a +2 charge, which is a 3-electron reduction. And on the oxidation side, you would have copper 0 going to copper 2 plus, which is a 2-electron oxidation. And then you can use the half reactions to actually work backwards to the balanced redox reaction. But ask yourself this question: are the atoms maintained first? And both of these half reactions have the appropriate number of nitrogen, oxygen, hydrogen in the reactants as in the products, or in this case, the 1 copper yields 1 copper 2 plus ion. So yes, the atoms are maintained. And then the second question is, are the electrons that are reduced the same number as the electrons that are oxidized? And the answer is no, because this is a 3-electron reduction and a 2-electron oxidation. So you can obviously multiply the whole equation up by the appropriate numbers so that you can get to a 6-electron transfer. And from there you can then just collect terms and write the overall balanced redox equation. And so these half reactions and the balanced overall reaction, this is what you need to do your battery work or to talk about the redox reduction. And this is fine, but just so you know, you don't need to go here, but just so you know, back to the general chemistry 1 concepts of a balanced overall reaction, there's kind of a mismatch in terms of net charge on both sides, and part of it you can kind of intuitively see right here, and that is that on this side I actually have the the nitrate came in the form of nitric acid, so you know that's actually 1 proton for every nitrate. So you can see right here there's actually a mismatch, but another way of looking at it is that the net charge on both sides is not equal. So if you look at the left-hand side, that's a +8 charge, -2 negatives, so that's a +6 charge. And on the product side, you basically got a +6 charge. So really, the overall charge is positive, and we know that you don't really have overall positive solutions. So what I've done down here just to explain it is to show you what happens in reality if you actually add 8 equivalents of nitric acid to 3 copper 0 ions, then you'll basically form 2 nitrogen monoxide molecules. You'll have 3 equivalents of copper nitrate in solution, and then 4 waters will form. So all the important components that are used for the redox, which is what we would use when we're doing batteries or we're doing redox reactions, they're all in place, but what you see is you also have an additional balance made with the copper nitrates that explains what happens. And if you look at this, the reactant side and the product side is actually charged balanced to 0, and that is more realistic to what would go on. So the way you can explain that is that basically you have an additional 6 nitrates on the reactant side that also shows up on the product side, so they're neither oxidized nor reduced. They're just spectator ions, but they account for the net charge so that the solution in going from reactants to products is always charged neutral, and that's more realistic from a thermodynamic standpoint. So now you don't have to go into this next step. It's not necessary, because the balanced redox reaction is what you need to do your battery work and to do redox reactions, redox half reactions. How do you then get a balanced overall reaction if you don't have one of these tables in front of you? We have a method, it's called the half reaction method, and it basically, it divides the redox reactions into its oxidation-reduction half reaction, and this reflects the physical separation in a battery cell or electrochemical cell. It does not require that you assign oxidation numbers. Now, take that with a grain of salt, because you might have to do oxidation numbers to figure out who's reduced and who's oxidized. The half reaction is usually easier to apply if you're trying to solve in acidic or basic solutions, because it's hard to intuit what goes on in an acid or basic solution, but this method will actually cover that correctly. So this is Dr. T's method to balance an overall redox reaction. And the mnemonic is to split atoms. Oh, he adds base. And I've kind of highlighted in here the different steps. The first thing is, the split is split the reactions into oxidation reduction. That's where you do probably have to go back to oxidation numbers to figure out which is which. Balance the number of non-oxygen atoms. That's where the atoms comes in. So once again, the key is you've got to have the same atoms in the reactants and products, but in this method, all you do is worry about non-oxygen atoms. Okay? Are your irons, are your sodiums, are those balanced? So the next step is to balance the oxygen. You add water to the opposite side. You'll see what that means here in a second. You balance the H by adding the hydronium ion to the opposite side. You balance all the net charge by adding electrons. So this is going to be the step in which you actually account for adding the appropriate electrons to each half reaction. You're ready to then add the oxidation and reduction half reactions once you know that you have the proper number of electrons in play. And then the last step, this step 7, this is if the reaction took place in a basic solution, you add hydroxide to both sides to cancel the hydronium. So now this all may seem Greek to you, so let's walk our way through this. So for an example, let's actually do where nitrate is reduced to nitrogen monoxide and copper is oxidized to copper 2+ as our half reactions. So once the steps are split the reactions in the oxidation and reduction. So there's what we know. Assuming we didn't have the half reaction tables in front of us, we know that nitrate turns up as nitrogen monoxide and copper oxidizes copper 2+. So now let's walk our way through the steps and see if we can arrive at the same place we did earlier with the table in front of us. For each half, balance the number of non-oxygen atoms. So let's go over here to the left. In this case, we have 1 nitrogen, and on the product side, we have 1 nitrogen, so that's balanced. 1 copper, so that's balanced. So we move on to the next step. To balance the oxygen, add water. So now let's see what that means here in application. See how there's 3 oxygens on the reactant side and only 1 oxygen on the product side? Now let's add water, and that's going to balance it out. So now that we have 3 oxygens here and then 1, 2, 3 oxygens here, that's what that means. Now to balance the hydrogens we just created, we need to go to the back side, in this case the opposite side, in this case the reactant side, and add some protons. So I need to add at least 4 of those. So now everything's balanced. Next step, let's balance all the net charge by adding electrons. So now let's deal with what the net charge is. That's 4 positive and 1 minus, so that's a 3 positive. So I could balance that out such that it equaled the other side, which by the way is neutral. So I got to get to 0 on the other side. So what I have to do is add 3 electrons, and now the net charge on this side is 0 as it is on this side. Okay, so now let's go to the right, the oxidation half reaction. This is neutral as the reactant side, so the products could become neutral if I added 2 electrons, right? So that's how you add electrons to balance charge. And then the next step, which we know from earlier, is that you can't have more electrons in reduction than you have in oxidation, so you have to multiply through by in order so that you can add these 2 reactions together. All right, and now you can combine both reactions together and cancel anything that's equivalent on both sides, which in this case would be 6 electrons. So now you have your overall balanced redox equation, and this is what you can use in your batteries, and you have the proper half reactions on both sides. So once again, this method allows you to figure out how these would be balanced in an acidic solution and in a basic solution. So now let's go to the basic solution just to kind of get an example. And let's look at the reactions we're going to work on. And I've gone ahead and split them out for you. Okay, so the question might come to you in a different form where you have to split them, but let's walk our way through this. Overall charge here is -1. So if oxygen is -2 and the net charge is -1, in this case chlorine is a +1, so it's going from +1 to -1, so this is being reduced. This one is overall charge of 2-. I've got 4 oxygens at a -8 charge, so that must be a +6. So that's going from +3 to +6 in oxidation, losing 3 electrons. So you split the reactions into oxidation reduction. For each half, now don't go ahead and add electrons to this, it'll come. Balance the number of non-oxygen atoms. So in this case, what the non-oxygen atom, reduction side are chlorine, and they're balanced already. The oxidation non-oxygen atoms, not 0, but non-oxygen atoms, are chromium, and they're balanced already, so you move to the next step. To balance oxygen, add water to the other side. So now in this case, see, we have oxygen as reactant, so we have to put a water on the product side. And then we go over here and look at the chromium. I've got 4 oxygens in the product side, so I got to account for that in the reactant side. And then the next step says add or balance out the hydrogen atoms by adding the proton to the opposite side. So you go back over here to the reduction side. I got a couple hydrogen atoms here, so I need to add a couple protons on this side. And over here, it looks like I've got 8 hydrogens atoms, so I got to add 8 protons to the other side. Now balance all net charge by adding electrons. So once again, this is about charge. So I got 2 times positive 1, that's positive 2 minus 1, that's a plus 2. That has to somehow get balanced with a minus 1. So that could occur if I added 2 electrons. So plus 2 minus 1 minus 2 more, that makes a minus 1. So it's minus 1 on this side and minus 1 on that side. So that's balanced. Go over here to the oxidation. Looks like I got a net charge of a plus 3 on the left, reactants. I got a net charge of a plus 6 on the product side. So I somehow have to compensate for that with 3 electrons, and now these are both equal. And once again, the key is not to go to charge 0, but it's go to a charge that's equal. Next step, make sure that the number of electrons in reduction are equal to the number of electrons in oxidation by multiplying through both equations. Collect your like terms, and you now actually have the proper balanced redox reaction for chlorate reduction being coupled to a chromate plus 3 oxidation. This reaction would be balanced, except that you actually could cancel a few things out. See how you have 3 waters on the product side and 8 waters on the reactant side? We can clean that up and cut that down to 5 waters on this side. And see how you have an excess of 16 protons here and 6 protons on the reactant side? Okay, you can cancel 6 of those protons out. So now once you clean that up, see how that just simplifies down? That's going to just simplify your equation for the next step. And now, in order to make it occur in a basic reaction, all you have to do is add hydroxide to both sides in such a way as to cancel whatever protons are present. So, long story short here, there are 10 protons here, so I have to add 10 hydroxides to this side, to the product side, and 10 hydroxide to the reactant side. There you go. And now all you have to do is clean like terms. Now, there's one little trick that you want to remember when you clean these up. If I had 10 protons and 10 hydroxides, that would actually make 10 waters, and so that'll cancel out. Now, if I have 10 waters here and I still have 5 waters here, that would give me a net 5 waters on the product side. So when you clean that down, see how it came down to 5 waters on the product side? Chromates are the same, the chloride ions are the same, the net 10 hydroxides is there, there's 2 of these chromiums, we got rid of the waters, right? We canceled those with this, and then the 3 ClO minus ions that are present in the reactants. So here is a balanced redox equation that took place in a basic solution. So here's an opportunity for you to practice, and you can see from the questions that you have these already combined. Kind of a first attempt has been made to make a balanced redox reaction, but these are taking place in an acidic solution, so you're going to have to apply your methods, break them back apart, balance them according to the mnemonic I taught you, then reassemble them into a balanced redox equation, and then do the same for the second expression in a basic solution. So at this point, stop your video, try and solve these 2 problems, walk your way through the mnemonic. If you have to, back up and look through how I did that again. And then when you're ready to check your answers, restart the video. So let's see how you did. First, we're going to work on that first equation. So if you look at the first half reaction, if you do the numbers, that's an overall charge on this thing is -2. You take oxygen times 7, the -2 times 7, that's -14. So whatever's on this side must be a +6. So that's chromium +6 times 2, that's 12 minus 14, that's a -2. So you go from +6 to +3, so that's a reduction. So now we have the iodide ion going to I2, which that would be losing electrons to go from -1 to 0. So that would be an oxidation. So we have those split into the half reactions. Now what we need to do is balance the atoms and charges in each half reaction that are non-oxygen atoms. So in this case, you would actually need a 2 with the chromium ion to balance out the 2 chromiums in the original Cr2O7 2- ion. You need to balance out your oxygens by adding water molecules. There you go. So 7 waters on the right would balance that out. Balance the H atoms by adding the hydronium ions to the other side. Then you balance the charges by adding electrons. So once again, this is balance the charges to each other. The reactants to the product side is what the method is calling for. So that's 14 positives, 2 minus, that's a plus 12. Meanwhile, over here I got a plus 6. So I got to add 6 electrons. So that's all good. And this takes care of the reduction half reaction. Now let's go over to the oxidation half reaction. Let's balance the oxygen or the atoms, and this makes sense. I had to have 2 iodine ions in order to make the I2 diatomic molecule. There are no oxygen atoms to balance out, so we can just basically start doing charge balancing by adding electrons. In other words, there's no oxygen or hydrogens that need to be added. Take care of that. And now the last step before we combine these together, this involves, if you look up here, it involves 6 electrons in the reduction side and 2 electrons in the oxidation side. So I got to multiply through on this reaction by 3 in order to make that balance. If you multiply through, you're going to basically have enough electrons to compensate. And so now you're ready to add these things together. So, here's the reduction half reaction, and here's the oxidation half reaction. You stack those up, and you're going to actually start adding them together, cancel electrons. It doesn't look like anything else cancels. You bring down your terms that haven't canceled, and there's your balanced overall reaction. Now let's look at the next one where you're actually doing redox in a base. Okay. Divide into 2 half reactions. In this case we have permanganate going to manganese dioxide, and this is an oxalate anion that's going to our carbonate. So let's start with balance the atoms other than O and H, and in this case the manganese is fine. On the right hand side it looked like we have to take care of a couple carbons. Okay. Balance the oxygen atoms by adding water to the opposite side. So in this one it's interesting. You'll look and see that we actually have just 2 extra oxygens than we do over here on the product side. So in this case it looks like we have 4 oxygens, and on the product side we actually have 3 times 2, which is 6 oxygens. So we're going to have to add waters accordingly. Balance these hydrogens that have now been added in by adding the hydronium ions to both sides. Now I want to remind you again that basically what we're doing in these steps is the exact same steps we had been doing if it had been in an acidic solution. The only difference really that's going to occur is in the very, very last step. That's going to make it different. So this looks just like what we would be doing if it was in an acidic solution. You balance your charges by adding electrons. And at this point we have 3 electrons in reduction and 2 electrons in oxidation, so you got to multiply through to make sure that they're balanced. In essence, trying to get to 6 electrons in each side. That's what that would look like. Now once you have these balanced in terms of charge, you are able to actually stack and add the equations together. That'll get rid of the electrons. Looks like we can get rid of some other things. We got protons on the reactant side and protons on the product side. We have waters on the reactant side and waters on the product side. And consequently, the result is, when you collect like terms, 2 permanganates, 2 waters, 3 oxalates will give rise to 2 manganese dioxides, 3 carbonates, and 4 protons. Now, once again, this is a balanced redox equation in an acidic solution, but the question asks for a balanced redox equation in a basic solution. So now all you have to do is apply that last step. And that step says add hydroxide to both sides to neutralize the protons. So in this case, we had a net of 4 hydronium ions on the product side, so we add 4 hydroxides to both sides. Remember that the protons and the hydroxides combine to make waters, and then you can cancel any common waters that you have. Collect like terms, and there you go. There's your balanced redox reaction taking place in a basic solution. Now, the last thing I want to do is just quickly show you this original acidic equation, and I want to show you that if you had your half reaction tables in front of you, how that you could simply quickly go to the table and get a balanced equation, because the tables already assume you'll be able to find them with and without acid and base added. So in this case, let's look. What we're looking for is obviously the reaction. If you look overall, it took place in an acidic environment. Okay, so we're looking for one of these species or both to take place in an acid. So now we just go to the table. We find, oh, okay, here's our reaction where the chromate ion gets converted over to chromium 3+, and that's taking place in an acidic environment. And also take note of the fact that it is lined up properly in reduction form, because these are reduction half reaction tables. So then we just got to simply scan down and find the iodine reaction. And as we suspect, we're going to want to run this in reverse, because you basically, this is the reduction, the one below it's going to be the oxidation if it's going to be spontaneous. Now in this case we don't have enough electrons, so all we do is just take whatever's on the half reaction table and multiply it through and flip it, and then combine the 2 reactions. So we can take what we have here where we've multiplied through and stack it with this, and you basically have the proper overall balanced equation much quicker than having to use the mnemonic. Now this is instructive just to kind of show you what I mean, that basically you can look on a table and see, in this case we're going from doing reductions with the permanganate ion, and you can see that in acid you get a certain product at one potential, and in base you can actually get a different product at a different potential. And that just kind of reaffirms that idea that, look, when you run these things in acids and bases, you get different products, and they occur at different potentials. So anyway, I hope this has helped you understand how to use this method to balance redox equations. I hope it also helps you understand the difference between these half reactions and balanced redox reactions that we use so extensively in battery work and in redox chemistry, and how that differs slightly from a balanced overall stoichiometric equation like what we've used in General Chemistry 1, which is very useful to do stoichiometry, and it's very useful to also ensure that you have charge balance in your solutions, probably more realistic to what you would add in a solution. I hope this helps you with these sorts of principles, and also it being able to do the half reaction method to balance a redox equation.